Hi, my name is Edouard and I will present to you my work at the Tech Lab in Sorbonne on quantization. It's called SPIQ, Data-Free Per-Channel Static Input Quantization, and we will tackle one very specific problem in quantization. So what is quantization and why do we care about it? Well, for the most part, deep neural networks have grown exponentially large in the past few years, especially in computer vision and natural language processing. And this growth has a cost, essentially a computational cost, which translates in higher power consumption associated to neural network inference. So here we can see the expected power consumption growth for the cloud computing. And in general, we can see that neural network will consume more and more in the future years. So quantization addresses this problem by simply changing floating point operations into integer operations and going from large number of bits, 32 bits usually, to a smaller representation going from 8 bits to 4 bits and even sometimes binary quantization, so 1 bit. So what about SPIQ and what do we address? Well, in general, activation quantization is often overlooked in the literature, while it is of paramount importance, especially in terms of accuracy. So what we can see here in the light blue values is the accuracy of what we would call the standard way to perform activation quantization. And in dark blue, we show the benefits of using SPIQ instead of the standard approach. So as we can see, those benefits are quite significant, and we will see how we can achieve those. So usually, as you may know, quantization can be achieved on the weights in a per tensor or per channel fashion. So what does that mean is the scaling factor for the weights is either a scalar in per tensor quantization or a vector in per channel quantization. Here in the standard quantization equations, we can see that the scaling factor of the inputs is constrained and has to have a cardinality of 1. In other words, it has to be a scalar. Right. How can we achieve per channel input quantization? Well, with SPIQ, what we propose is to simply hide the dequantization step of the inputs inside the weights of the channel. So this, in other words, instead of having a dequantization outside of the product, it is hidden in the full precision weights, which will update their scaling factors. So this allows us to maintain the benefits of static quantization while achieving higher precision, especially higher precision than dynamic quantization. So to test that, we simply added the SPIQ input quantization and activation quantization to some standard state-of-the-art quantization schemes and demonstrate the benefits from it. So as you can see on ResNet 50, where the schemes already work pretty well, those results are not quite impressive, whereas on other convolutional networks such as MobileNet and EfficientNet, who are known to be very difficult to quantize, we can see that there is a huge benefit from a better activation scheme, as we get a bonus of 8 points in accuracy and even 20 points on EfficientNet. So here what we show are the effects on the feature maps, and as we can see, the information is much better preserved using SPIQ rather than dynamic or static quantization, especially when we have a data-free scheme. Thank you for your attention, and I wish you a very pleasant conference.